In the previous section, we looked at asynchronous counters, and recall what an asynchronous counter was. It was a counter, and remember that we had a clock pulse coming in, and that clock pulse was simultaneously fed to all of the flip-flops in the given circuit, and all of the flip-flops changed state at the same moment. With an asynchronous counter, and the asynchronous simply mean that they're not in sync with each other. And so the way that these will work is here we have the clock impulse, the clock pulse coming in. And notice this is not going anywhere. This particular line over here is just going over to the logic analyzer to display it. So the only input is going to this first flip-flop. And this flip-flop, as this clock, as it changes state, the Q output is fed into the next clock input on the next flip-flop, and it will cause this one to change state. So we'll have a change in state here, which is fed to the next one, and then this changing state here, and it'll fed to the next, to the next, to the next. It's kind of like the dominoes, you know, one falls and then they just fall in order. These they work well. There's really not a problem with these, except that at higher frequencies they can become problematic, and it's because of something called propagation delay. And propagation delay, your text mentioned it earlier. I didn't mention it then, but I will mention it now. Propagation delay is the time that it takes a signal to move from the input to the output. Now, typically we think of that as being instantaneous because it is so rapid, but actually it does take an amount of time. Now, typically it's measured in nanoseconds. I mean, you may have a gate that has, you know, maybe 3 nanoseconds from the time it goes from input to output, which isn't very long. However, if you have, in this case, 3 flip-flops, well, then it's going to jump up to 9 nanoseconds. The propagation delay, and that's what they call delay, from the time of the input till the time of the last output, in this case it'd be 9 nanoseconds. But if we have a large circuit, say we have 20 or 30 flip-flops in a row, then suddenly the nanoseconds begin to count up. And if we have a high-frequency input, there is the very real possibility that you begin to send pulses in, and before you get to the end of the cycle, before it's completely clocked, a new cycle is occurring. And so in this case you can lose counts and it can become problematic. So for this reason, the synchronous variety of counters are actually more popular. Now, we're not going to go into the detail that we did in the previous circuit addressing counting. What we will do here, I do want to mention this is actually the spectrum analyzer display, and these are the 3 the display we had to see. This would be the C, B, and the A input, and this is the clock down here. And so let's look at the how this one actually counts, because this one, the previous one that we had looked at was an up counter. This is actually what we call a down counter. This is something that counts down from a specific value. And so in this one, if we look at the inputs here, we'll see you have a low, low, low. That would be 0. And then when it resets, it jumps up to high, high, high. That would be 7. And then here we have a high, high, low, which would be 6. And then a high, low, high, which would be 5. And then 4, 3, 2, 1. And at this point, we're 3 lows. And then here we reset to 7. And so this is a down counter. And if you want to do the simulation on this, look at that a little bit closer. It is circuit 15 underline 29. Integrated counters are very commonly used, and they come in many different configurations and with many different counting sequences. And they will include counting in binary as well as BCD. And with a binary counter, you know the counting sequence, you'd have 0, 0, and then you'd have 1, and then you'd have 2, and this is the way it would display in binary. This is all well and good if you understand binary. I had a student one time build a binary clock, and it displayed in binary, and it was kind of interesting to watch, but if you wanted to figure out what time it was quite challenging, because he had an hours, minutes, and seconds LED display, but it was all in zeros and ones, so it was quite an awkward clock, though it was very interesting. But this BCD, this is binary coded decimal. So what this would do, it would take that, you'd have all your binary counting, but what it does is it would display it in decimal, so it is more understandable. Now, this particular device here, this is an integrated counter. By integrating, what they mean is here you have a single chip, and this single chip could contain 40, 50, 100 flip-flops possibly, and it's all on the single chip. So rather than having this long circuit with 20 or 30 flip-flops and AND gates and OR gates and whatever, you just simply have an integrated chip that does the same thing. You don't see all of the flip-flops, but you just plug it in, and in this case here we have a signal generator input, and then our outputs here are simply in this case the 4 bits. Now I have on this next screen, we see this is the same circuit, and this is a display of the outputs that would come out of it. Now recall, we mentioned earlier about how that the counters will count, but the way that they count is they actually do it by means of frequency division. And this is another common use of counters, by the way. In this particular case here we have a 32 megahertz input, and the outputs would be 16, 8, 4, and 2. And so systems like this are commonly used in computer timing systems. Is just one example where you have a given frequency that the computer operates at, and then you need lower frequencies for various buses, and oftentimes you want the buses to be synchronized together, but they operate at lower speeds. So this would be one way to do that, to have differing frequencies but have the frequencies actually sync together. And so anyway, that's another use for frequency division in computers. This is a student project. A guy named Brian Norton was in my class a while back, and he built a student project. This is it right here. This we jokingly referred to it as Brian's bomb, because it looked kind of like some kind of a explosive device. It had it had the readouts here, and this thing would count down or count up. You could do lots of different counting sequences, and then he had some connections here where you could connect something, and at the end of the counting sequence it would actually do something, most commonly to activate an alarm or set off some type of not a bomb, okay? But that's anyway, we kidded him about it because it did look like a bomb. Anyway, so this is a device, rather sophisticated device that utilized counters. And he had several integrated counters built within this device. Then this final circuit is a state machine. This state machine utilizes flip-flops. It is a 3-input entry system. If the correct sequence is entered, the solenoid will activate, granting access. And so here we have this circuit. You'll notice over here on the far left side we have switches S1, S2, and S3. And if the correct sequence is entered here, then this solenoid will activate, and in this case it could be to grant access. Brink's home security systems are activated and deactivated with a system similar to this. If you've seen Brink systems, they have a keypad, and in order to turn them on you input 3 values, and if you want to deactivate them you enter 3 values. Also in this particular circuit, whenever you press a key, the little LED down here will activate. We're not going to go into the theory of this one. This particular circuit is in your circuit package, and I do invite you to play with it and it does utilize a couple flip-flops. Okay, in this section we're wrapping up our discussion on counters. We ended with the state machine. We looked at a student project. We looked at the concept of frequency division, and we talked about integrated counters, which are probably the most common building block that you would use just today to build counters. Then we looked at asynchronous counters, and that concludes our discussion on counters.